All right, in this video, we're going to very quickly review doing budget lines, just give you a couple of things to remember and think about, and then we're going to do a whole pile of utility maximization problems very quickly. So make sure you have your calculator, make sure you have this handout in front of you with the pencil and a ruler, and you are ready to go. Let's dive in. So what we've previously been focusing on is the preferences half. What's going on inside the human being's head that generates the things that they prefer more than other things? The baskets, the collections of goods they like better than other groups or collections of goods. Here we're looking at what we call the opportunity set, or sometimes I'll call this a consumption possibilities curve. It's kind of like a production possibilities curve, except it's normally a straight line, at least in the simple cases we'll look at. But the opportunity set tells us what are the things the person can actually buy, and then when we maximize utility, we're using math and a graph to try to pick the things that maximize that person's happiness. When you look at a budget line, we'll often call the slope of a budget line the marginal rate of transformation. The marginal rate of transformation, think about it as meaning at what rate can I substitute one good for another in my shopping cart if I were in a store. So for example, if eggs cost twice as much as cookies, say eggs are $10 and cookies are $5, if you put back one batch of eggs, that's $10 that it frees up, and that would allow you to get 2 boxes of cookies. So marginal rate of transformation, the slope of a budget line, tells you about at what rate you can switch between goods. This slope of a budget line, also you can think about it as telling you the opportunity cost of good X. So as you move along the x-axis, increasing the amount of X you would like by 1, the slope tells you how much Y you have to give up in order to get 1 more X. Contrast this with the slope of an indifference curve, where the slope of an indifference curve, the marginal rate of substitution, tells you at what rate the person is willing to trade Y's to get 1 more X. The marginal rate of transformation is at what rate you have to trade Y's for X's according to the prices. So it's the rate at which you can swap buying one item for another. When we graph a budget line, a few things to think about. Number 1, it's going to have this equation. The amount of money you have is the budget, and that has to equal the price of X times how many X's you're buying, plus the price of Y times how many Y's you're buying. To graph it, the easiest way is to connect these 2 points, the budget over the price of X and the budget over the price of Y. Let's go ahead and do that so you can see how that works. So suppose we had $200 in our pocket, and we were going shopping, and X's are $10 each and Y's are $5 each. The easy way to graph a budget line is just to figure out what's the most X I could buy with $200 if I bought no Y's. And the way to do that is to do this kind of formula. $200 divided by $10 tells me that I could buy 20 X's, assuming I didn't have any money left over to buy Y's. And then we want to find the other extreme point. What if I spent all my money on Y's, then $200 divided by $5 says that I could buy 40 Y's. Again, that's assuming that I didn't spend any money on X's. Now if we go to our graph down here and we plot those 2 points, of course we're going to put X's on the x-axis and Y's on the y-axis. Then we figured we could buy 20 X's if we spent all our money on X. So this point says one thing we can afford is to buy 20 X's and 0 Y's. The other extreme point, we could buy 40 Y's, but that point assumes we're buying 0 X's. And now if we connect those two with a straight line, we have a budget line. There we go. So this is our budget line. If our budget is $200, the price of X is $10, the price of Y is $5. One other thing I want you to notice is a shortcut way to find the slope of this line that we will use very often is the slope is minus the price of X over the price of Y. In this case, without having to take the time to graph the line, we could say that the slope of this budget line is minus, because it has a negative slope. The price of X is 10. The price of Y is 5. So the slope of this line should be negative 2. This is a very useful shortcut. Let's verify that that is indeed the slope of this budget line. Yes, if we zoom in, we can see that every time we want one more X, we lose 2 Y's. Want one more X, we lose 2 Y's. And why is that the case? It's because the prices of X are higher than the price of Y's, right? Every time I want another X, I need $10, then I have to give up the opportunity to buy 2 Y's, which would also cost $10. A couple of other things we want to do when we think about a budget line is, of course, number one, just think about what it is again. It is the set of all the possibilities of what we could buy, a consumption possibilities curve. We can't afford anything out here because we don't have enough money to buy it. We could buy things that are inside the line, but then that would mean we have money left over. And we're going to assume that we're going to spend all of our money in this context. We could change that in a more complicated example. But as long as we're somewhere on this line, it means we're spending all of our budget. We want to be able to visualize quickly and really understand what happens if our budget goes down, but the prices stay the same, right? So if our budget goes up or our budget goes down, but the prices aren't changing, what happens to a budget line in that case? Well, now our endpoints are going to be 150 divided by 10 equals 15, and that tells us how many X's we could afford, and 150 divided by 5 equals 30. That's how many Y's we could afford. Let's graph this budget line and see what happened. Okay, so there's 15 on the X-axis, and there's 30 on the Y-axis. Connect those with a straight line. What do you see when you look at this? Well, you see that the purple line with the lower budget is parallel to the orange. The slope didn't change. Why didn't the slope change? Well, remember that shortcut formula for getting the slope? The price of X divided by the price of Y, right? Now it's negative. When we do the math later, we're going to think about it as just what's the absolute value, but it's negative. But since the prices didn't change, the slope's not going to change. We know it's a parallel shift. But what kind of shift is it? Well, it's a shift inward, reflecting the idea that we can't afford as much stuff as we used to. So it's a shift toward the origin. Our opportunity set has decreased. Our resources for affording to buy things have gone down. Now let's do this last question to picture what would happen if the price of Y increases to $10. How does that affect our opportunity set or our budget line here? Well, let's assume that we're starting from this point here where we had $150. Then if the price of Y goes up, the amount of X we can afford isn't going to change. And so all we need to do is calculate $150 divided by 10. Oh, that's going to be 15 as well, just like the Y's over here. So let's draw that. Basically, when the price of Y goes up, we can't afford as many Y's as we used to. And we draw our budget line. And now we see that the slope did shift. What is that slope now? -1, right? Because the price of X and the price of Y are the same. That -1 says that every time you'd like another X, you have to put back 1 Y. Want another X, you have to put back 1 Y. This price increase also reduced our opportunity set. It reduced, cut out a lot of combinations of X and Y that we used to be able to afford. So that's also going to make us less happy. So to sum up, the slope of a budget line you can find very quickly by the price of X over the price of Y. And a parallel shift is what happens when you get more money or less money, keeping the prices constant. But when you raise the price of a good, it's going to reduce your opportunity set by tilting in the budget line either one way or the other, either down the y-axis, or if the price of Y went up, or if the price of X went up, the budget line would slide in the x-axis here, making it steeper, right? All right, now let's jump into maximizing utility. This is a fundamental skill that we're going to use in many applications later on. Okay, problem number 1. What we want to do is find, out of all the things the person can afford, what's the one that gives them the highest utility. There are 2 equations that describe what's going to happen in this case. Number 1, the budget equation describes all the things we can afford. Now, if we pick from all the things we can afford the thing that maximizes our utility, then this first equation is going to guarantee that we've picked the one that maximizes your utility. What this equation does is make sure that the slope of the indifference curve, the marginal rate of substitution, is equal to the slope of the budget line. And that means we're going to be on the highest indifference curve that is just barely tangent to the budget line, touching it at 1 point. Let's see how this works. So let's suppose that our budget is $60. Price of X is 10, price of Y is 15. Let's graph the budget line first to see what's going on. Doing this, we can get an approximate solution, and then we can do the math and verify and figure out exactly what the correct solution is. So graphing this budget line, just like we were doing before, if we spent all our money on X, we could buy 60 over 10 X's, which would be 6. All right, so let me graph that on the x-axis. And if we spent all of our money on Y, 60 divided by 15, we could afford to buy 4 Y's. Connecting those with a straight line. Now, if we were just going to guess, what's the highest utility we could get? And how many X and Y should we buy? And we weren't allowed to do any more math, or we didn't know how to do any more math. What we would do is look at our legend here over on the right-hand side and say, okay, well, we have indifference curves here for a half, 1, 1.5, 2, right? Going up from the bottom, we know we could get 1/2 of a util here, or all the way up on this side over here, we could get 1 util if we bought this basket down here, or if we bought this basket way up there. We could get 1.5, or 2, or 2.5 utils, but we could get higher than that. Now remember, when we draw these indifference curve maps, we're just drawing a few of the indifference curves here for every half of a util, but there are indifference curves for every possible value. We're just plotting a few of them. So there's going to be an indifference curve that looks like these other ones, that has the same kind of shape. So in between this gray one and this bluish green one, there's going to be another indifference curve here that does something like this and is just tangent at 1 point. That means it's going to be the highest indifference curve we can afford to get to. And then it's going to kind of curve down something like this. Why do I do this? Just to give us a guess at approximately around where our optimum basket and our maximum utility would be. We can't pick an exact number, but our optimal solution is going to be somewhere around here, and it's going to be one of these points on our blue budget line, right? So if I had to pick, it's going to be something in this neighborhood. The amount of X looks like it could be 1 or 1.2. And the amount of y looks like it could be 3, 3.2, or 3.4, somewhere in that neighborhood. This is an initial guess. The math will tell us the right answer. How much happiness do we think we could get after we solve this problem? Well, we know we can get more than 2.5 utils because that's this gray indifference curve, and we know we can get beyond it. We know we can't get 3 because that's a little beyond our reach. So somewhere between 2.5 and 3, maybe 2.7, 2.8. We'll find out in a minute. So let's solve these two equations after we set them up. Now we're going to use the shortcut rule for marginal rate of substitution that we've talked about before. If we have a Cobb-Douglas utility function, which we do here, u equals x to the 0.2 times y to the 0.8, the shortcut rule says take the exponent on the x, multiply it times y, divided by the exponent on the y times x, and let's set up our first equation that we're going to need. So equation 1, it's going to be 0.2y over 0.8x. That's the marginal rate of substitution function. We want to set that equal to, since that's the slope of this orange unknown indifference curve, we want to set that equal to the slope of the budget line. Price of x over the price of y. Okay, that's 10 over 15 equals 10 over 15. That's equation 1. Equation 2, the budget line equation, just says take the budget, $60, and that's got to be equal to the price of x, $10 times x, plus $15 times y, and that's our second equation. Our goal usually is going to be to take this first equation and solve it for y, and then plug that in to the budget equation for y, and then solve for x and y and see how much utility we'll get. So let's concentrate on equation 1 here, solving that for y. Normally, before I even get going, I like to just simplify a little bit to make my math just slightly easier. So I know 0.2 over 0.8 is 1/4. So I could rewrite this as y over 4x equals, and I know that 10 over 15 is 2/3. You don't have to do it this way, but I like to simplify whenever I can see an easy way to do it. And then we want to multiply both sides by this 4x. So 4x over here. This 4x on the left will cancel. And then we'll just, simplify this. 2/3 times 4 is 2.66666666. So our result here, y equals 2.67 if we round off x. Now what we want to do is take this, now that we know that that's what y equals. And what this equation is telling us is, at the optimal solution, we want to buy more y than x. 2.67 times as much y's as x's. So if we were buying 1x, we'd buy 2.67 y's. See? But we want to plug that into our budget line equation to see what pops out. So we're going to write 10x plus 15 times y. Well, y is 2.67. X equals 60. We want to simplify this to see how many total x's we have. So we have 10x plus 15 times 2.66666666 times 15, and I'm getting 50. So on the left side we have 50 x's equals 60. Therefore, x equals 60 over 50, or 1.2. Now, what I like to do now is look at the graph and say, is that what I was expecting to get? And when we look over here, it was, right? We thought that the amount of x in that little region there should be around 1.2, and that turned out to be what it was. And now we want to figure out how much y. Now we can see from the graph a little more precisely that it's probably around 3.2. but let's do the math to check. Now, the easiest way to figure out how much y is always going to be to go back to this equation. Y equals 2.67x. So we just take our 1.2 and we multiply it by 2.67. So 1.2 times 2.66666666. And yeah, we're getting 3.2 there. Maybe with a little bit of rounding, right? So y equals 3.2. And now the last thing I always want to know is how much utility are we going to actually get? And to do that, we go back to our utility function right up here. And now we know that x is going to be 1.2, raise that to the 0.2 power. Y is going to be 3.2, raise that to the 0.8 power. And that'll tell us how many utils of utility this person would get. And remember, we thought it would be somewhere between 2.5 and 3. And I'm getting 2.63 equals 2.63 utils is how much utility this person will be able to get. And that all checks out with what the graph was suggesting we could probably attain with this budget and those prices. Once you kind of get this idea, it's important to practice, practice, practice. So let's go to the next problem here. Now I want you to pause the video, set it up, and see what solution you get. I'm going to come back and I'll present my results. Now keep in mind, all we're changing here is the utility function. Now we're dealing with x to the 0.5 times y to the 0.5. We're keeping the budget and the prices the same. So equation 2 is going to be the same. 10x plus 15y equals $60. It's just equation 1 that's going to be changing here. And it's just the marginal rate of substitution that's going to change because the slope of the budget line will still be the same. The budget line, in fact, isn't changing because the prices and the budget will be the same. So draw the same budget line we had before. Our first equation is going to be the marginal rate of substitution equals the price of x over the price of y. So I'll help you get started with this one. So the price of x over the price of y is still going to be 10 over 15, which we said up here we could simplify to 2/3, right? So we could go ahead and write equals 2/3. And now we just need to see what's the marginal rate of substitution going to be using our shortcut rule. It's the exponent on the x times y divided by the exponent on the y times x. We're going to end up with 0.5y over 0.5x, but of course those 0.5s are going to cancel. And we want to solve that for y. Okay, that's easy enough, right? Y equals 2/3 x. So again, this equation here tells us we're going to buy less y than x. Take how many x's we're planning on buying, multiply it by 2/3. That tells us how many y we should buy to maximize our utility. So plug this in here, graph your budget line, make your guess, find your real answers for utility, how much x and y, and then I'll show you my answers. All right, from drawing my budget line, I made my guess. I thought that the solution for x and y would be somewhere in here. That would be somewhere close to, let's see, 0.51, 1.5, 2, almost 2.5 utils. And it would be somewhere around 3 x's and around 2 y's. And indeed, that is what we got. So when we plug this in for y, we get 10x plus 15 times 2/3 y. 15 times 2/3 is 10. So we get 20y equals 60, y equals 3, x equals 2. Now how much utility will we get? Well, let's plug that back into the utility function here. Utility equals 2 to the 0.5 times 3 to the 0.5. And we get, yeah, something really close to 2.5. 2.45, something like that. So you can see we are really close to that indifference curve for 2.5, but not quite getting there. So if you understand the basic setup about how to write the two equations down, solve for y, plug into the other equation, should be fairly easy. It's just algebra, and the algebra isn't even that hard. Let's go on to our next problem here. Again, if you want to understand how to do this, pause the video and do it. Again, everything's going to remain the same. To keep it simple, we're only changing the utility function, and therefore the indifference curves are going to look different here as well. So I've copied down the equations from up above. What you have to figure out, though, is what goes here and here. How's it going to simplify? Then solve for y, plug it into the other equation. I'll pause now. All right, so again, I made my budget line, and it looks pretty darn close to where we can see where we're going to end up here. This light blue indifference curve gives us a utility of 2.5 here, right? 0.5, 1, 1.5, 2, 2.5 utils, and it looks like it's going to be right around 4 x's and 1 point something y's here. When we solve for y, we get y equals 1/3 x. And sure enough, we solve and get x equals exactly 4, y equals 1 1/3, and that gives us just over 2.5 utils. So I guess when we're looking at this and we zoom really in, even though it's hard to tell, especially when you're drawing things by hand, that we are able to find a point just on the other side of this indifference curve. But it's so close that, it's impossible to tell just by using your eyes. Very cool. All right, I want to work one more problem here. What happens if we don't have a Cobb-Douglas utility function? What do we do then? Here's an example of a quasi-linear utility function. In this case, you can't use the shortcut to find marginal rate of substitution. You have to fall back on the idea that the marginal rate of substitution is the marginal utility of x divided by the marginal utility of y. And remember that the marginal utility of x is the partial derivative of the utility function with respect to x, and the marginal utility of y, similarly, partial derivative with respect to y. So with this additive quasi-linear utility function here, the partial derivative of the utility with respect to x, remember we just take the derivative of things that have an x in them, treat y just like it's a constant, like the number 5. So x to the 0.5, the derivative is 0.5, x to the minus 0.5, plus the derivative of a constant. Okay, 0. And then the partial derivative of the utility function with respect to y. Well, that x part, that's just a constant, so that's derivative 0. What's the derivative of y with respect to y? It's just 1. So when we get our marginal rate of substitution function, we're going to take our result for marginal utility of x, divide it by marginal utility of y, and we're going to end up with marginal rate of substitution just equals 0.5 x to the minus 0.5. Period. Divided by 1, right? But that doesn't do anything. So what's going to happen in this case? Well, again, we're keeping the same budget, same prices, so let's just draw our budget line and see what it looks like might be going on in this case. Let's see. Here we go. And notice how these indifference curves do cross the x-axis and do cross the y-axis here. So where does it look like we'd get the highest utility? Well, it looks like we can get a little bit beyond this bluish one here. And if we look at our legend, we'll see. 1, 2, 3, 4. Okay, so we're getting a little beyond 4 utils. And if I just had to guess, I'd say maybe our optimal solution would be somewhere in the middle there. Let's do the math and find out. Okay, let's set up our two equations. Equation 1 says we want the slope of an indifference curve That's the marginal rate of substitution, 0.5 x to the minus 0.5, set equal to the slope of the budget line. That's the price of x over the price of y, 10 over 15, or 2/3. Second equation, the budget line, 10x plus 15y equals 60. So what I would do here is think about multiplying both sides by 2, and 2 times a half just becomes 1. And then we're left with x to the minus 0.5 equals 2/3. But we have to remember multiply both sides by 2. So that leaves us with 4/3 over on this side. All right. So now what we want to do is get rid of that negative 0.5 exponent. And the standard rule for getting rid of an exponent that you don't want is to raise both sides to the inverse, or the 1 over that exponent. And so if we want to get rid of 1 over minus 0.5, minus 0.5. Now to do this, you can just do this in your calculator if you want. Or if you want to simplify things slightly before you do that, you could say, well, 1 divided by a half is 2, but that's negative 2. So what we're really calculating here is 4/3 to the minus 2 power. So let's put that in our calculators here. 4 divided by 3 in parentheses, raised to the minus 2 power. And I'm getting 0.5625. And that's our answer for how much X this person should buy, 0.5625. Now let's just double check that that's somewhere in the neighborhood of what we were looking at on the graph here. Well, that's kind of on the outside range of where I was guessing, but it could be right. Now what we want to do is plug this in to our budget line here for X. And it's really interesting to think about what this is doing and not just go through the mathematical steps without thinking about them. Here what we're doing is we're saying, well, if I buy 0.5625 X's at $10 each, so 10 times 5.5625, that's going to equal $5.63, right? Let's just keep all the decimals here. And then if I add to that how many Y's I buy at $15 a piece, that's got to add up to $60. Now this next step in the algebra is just figuring out, well, if I'm spending $5.62.5 on X's, how much money do I have left for Y's? We subtract that from both sides. So it cancels over here. Minus 5.625. So now we have 15 Y's. How many Y's I buy at $15 a piece? I'm going to be spending $54.37.5 on them. And divide both sides by 15. Y equals 3.625. Now let's calculate how much utility that would give us. So we're going to have the square root of X, and that's that 0.5625 square root, right? Plus Y, 3.625, 4.375. Utils. All right, now let's have a look at our graph and see if this looks like it's a plausible solution. So 3.625 Y's right around here. Yeah, so that's a little out of where I would have guessed, but the slope of this indifference curve and the slope of that budget line right there, they could be the same. And then that would put us at about a little more than a half of an X. Oh yeah, I guess I did draw that dot a little too low there. So let's adjust it. It needs to be a little bit above 3.6 there, right? And then that would put us just below 0.6 x's. I'll buy that. And we're getting almost 4.4 utils, so we're beyond this indifference curve for 4. We're not quite halfway to the next indifference curve at 5. So again, I can buy that answer. So I have some other examples on the sheet that you can practice. You can also make up your own, as long as you have some indifference curves and you make up a budget that is going to give you a solution within the indifference curves you have, then you can draw that budget line and you can work problems on your own, and you can be reasonably sure that you're right as long as your algebraic solution matches with what the graph is trying to tell you that the approximate answer should be. So I'm going to sign off here, and I'll come back later and we'll work some other problems on this handout. But this is Dr. Berkey signing off. As always, if you have questions, let me know. Otherwise, wish you the best of luck with your economic studies, guys. Talk to you later.